the wordings of your justifications and stuff like that. But this says that you've got a graph of G prime, and it wants to know what the inflection points of G would be. So first of all, how many inflection points did you find? Like, just literally how many?
3.
There are 3, agreed with you. So the locations of those would be x equals what, and what?
-1, 1.
Perfect. So we'll say G has inflection points at x equals -1, x equals 1, x equals 3. Because, why? What kind of a justifying statement would you say for any one or all of those, Santi?
Well, -1 and 3 changes, G prime changes from decreasing to increasing.
So did you guys notice he corrected his it? Well done.
Good job.
So at those 2 points you said G prime does what?
Changes from decreasing to increasing.
All right. G prime changes from decreasing to increasing. Okay. I think Santi has done a pretty good job with that. Does that make sense? I think his wording is fine. He's identified the right characteristic with, the right point. Is that okay? Okay, then we'd also want to include a statement about 1. So we'd say, and at x equals 1, what does G prime do?
Changes from increasing to decreasing.
The other way, yeah. Changes from
Very much.
increasing, decreasing. So please do attempt to identify the correct characteristic for the correct point. Don't just have some general, some stuff went from increasing to decreasing at these points, or vice versa. Like, try to be specific with what it is you're talking about and where it is this thing happened, whatever it was. All right. Question, yeah.
For the AP test, though, would it matter? If you
They
said
tighten it
that?
up pretty good. I mean,
Do they?
there is no when you become a reader, the thing you learn is that tests are not graded exactly the same way every year. I mean, it's like the theme of the grading is essentially the same, but every now and then you'll get somebody who's like, hey, if they say increasing or increasing to decreasing or vice versa, there will be some question leaders that are okay with that, and others are like, vice versa, no, we need to be specific. And so I always say to my own self is good math, and as long as you do good math, no one's going to be able to argue with you. If you start to pull back and say, well, what's the minimum I can do? That's when you start like getting into trouble with, well, there was a tough question leader this year, and the previous year they were kind of easy.
Yeah.
If you just use good communication and good math,
They can.
you'll be fine. There won't be any issues at all. Yeah.
Okay.
Okay, and then the other one, where's the graph of G, both concave down and increasing? So it's not asking for 2 different sets of criteria here. It's where are both of these things happening at the same place? So anybody want to explain what you looked at, what you did?
I looked for
Jeff.
where G prime is decreasing and it's positive at the same time.
Where G prime is decreasing and positive. So let's see here. Where is G prime decreasing? Well, it's decreasing there and there. And where is G prime also positive? Well, of course, that would be where I'm going with a blue highlighter up here. So I would say wherever the orange and blue highlightings intersect, overlap each other there, I'd say, Jack, you've identified a pretty good way of identifying those, and I think we're good, right? So intervals there would be, -4 to -2. That interval, and then 1 to 3. And then as far as, it doesn't say justify, but I'll go ahead and put the reasoning down, and I think the way that Jack started would be a good way for us to finish, right? We can say because G prime is both positive and decreasing on those intervals. Okay. Fair enough. We've covered a lot of ground in the last week or so. We okay with this? Okay, we're going to do a little shifting of gears. We'll go back to a little bit of max and min stuff here at the end, and then that'll probably be about it. So, the kind of the newish topic here has to do with limits. Of course, the phrase limits at infinity is a little bit misleading because you can't actually get to a place at infinity. It's should probably be better worded limit as we head towards infinity, something like that. And so horizontal asymptotes are always associated with this. I always call it like long-term behavior or end behavior, always associated with horizontal asymptotes. And really, if I said, hey, the far right edge of the graph, aren't we really talking about as x goes towards infinity? Or the far left edge of the graph, we're talking about as x heads towards negative infinity. We're just going to talk about some patterns and things that develop there. So look at the green graph up there and the blue graph. The green graph, as x heads towards infinity, from the graph, what would you estimate that limit to be? Negative 2. How about the blue graph as we head towards negative infinity? 4. Yeah, we're just talking about the long-term behavior. This, of course, does not mean that there's some y value out there where the actual graph hits y equals 4. We're just saying that's where we're headed towards as a general pattern to the far left or far right edge of the graph. Some basic fundamental concepts where if we can get these down, we can handle most of these, I would say. So if c is a constant and x is a variable with some exponent, like r, and x is heading towards infinity, so c is held constant, x is getting huge, what's the value of the limit? Approaching 0, yeah.
Wait, is it assumed that r can't equal 0?
So r wouldn't be 0 or negative. R wouldn't be 0 or negative. Yep. Good question. And then the same concept, if we're heading towards the far left edge of the graph, the denominator is getting to be a really huge negative number. We'd be approaching 0 from the other way, I guess, right? From the negatives. But we'd still be approaching 0, right? Negative 0, or 0 from the left, I guess, right? Would be maybe a way to think about that. As far as we know, there is no negative 0. I've never heard that. Okay, so let's take a look at a few examples, and so let's talk about two ways to approach these. There's really 3 ways to approach these. Y'all remember L'Hopital's rule? So most of these would be a good opportunity to use a L'Hopital's rule if you so chose, although it would not be the most efficient in most of these cases. We will get to L'Hopital's rule later where it is the more efficient and the way that makes it actually possible. But for now, we're going to look at this in a couple of different ways. Why don't I show you or remind you of, because I think most of you know this, the little pre-calculus trick that you can do with these. So with this first one, we're talking about long-term behavior. And you want to know the number one mistake that people make with these is they apply what we're about to talk about to the wrong situation. They don't look at the limit as x approaches whatever. They don't even bother looking at that. They just see some rational function over there, and they just apply the trick. And then later on they go back and like, oh my gosh, it was limit as x goes to 5. It wasn't even going towards, you know what I'm talking about? Like you just sort of skip the directions and you jump right into the meat of the details and you're like, oh man, it didn't even ask me to do the thing that I was trying to use the trick for. So do please pay attention to that. In any case, we are heading towards infinity. And here's the trick, right? What do you look at? Those maybe that remember this, what do you look at if you're trying to use the trick? Degree, yes. So you look at the degree of top and bottom. The degree of the top is a 2. And I'm looking at this. Oh my goodness, what did I just do? There we go. I'm looking at this 2 right here. So the degree of the top is 2. What's the degree of the denominator? 2. Also 2. We're looking at this 2 to decide that. So the trick is, of course, if the degrees are the same, like they are here, then what's the long-term behavior equal to?
You compare the coefficients.
Yeah, the ratio of the 2 lead coefficients. So you could, if this were just some multiple choice thing where you didn't have to show any process at all, I think we just go with the ratio of the lead coefficients, 1/2, you're done. Hopefully it took you like 9 seconds, right? If you've got to show a little bit of work, so this would be if it was not a multiple choice, so you had to show a little process. Here's one way to do it. Once again, you identify the degree of the denominator, and here's what you do. Perhaps you remember this. You take that degree of the denominator, and you divide the top and the bottom by that variable with that degree. So since the degree of the denominator is 2, I would divide everything through by x squared. So I divided the top, both terms in the top by x squared.
So it's by the bottom?
And by the degree of the bottom, yep. And I will divide all the terms in the denominator by the same thing. Bless you. So, of course, this creates a whole bunch of cancellations. So in the numerator, I would then get the limit as x approaches infinity of 1 plus 3 over x squared over 2 minus 1 over x squared. And this is where those little fun facts about these limits comes into play. As I apply my limit, what's going to happen with this term? Approaching 0. Same thing with that term as well, right? It's 1 over a gigantic number getting bigger and bigger and bigger. We're heading towards 0. So this would technically equal 1 plus 0 over 2 minus 0. And there's, once again, our 1/2. We actually showed a little bit of process there. So again, like the question always rises, when do I have to show my work and when do I don't? Well, if it's multiple choice, I'm not going to be going through your work and looking for all these quality steps. So if it's multiple choice and you feel like you could use a pre-calc trick, do it, please. But if it's a free response and it says, hey, show your process, show the steps leading to your answer, that kind of thing, then you'd have to do something like this. Or if you already know L'Hopital's rule, you could do that too. Or later on, if you learn L'Hopital's rule, you could use that when the time comes. Fair enough?
Yes, sir.
Okay. Well, let's see if you guys can handle the rest of these. Take a few minutes, look through those. You can use, I would say, practice what you need to practice. If you feel you're good and just want to use some pre-calc trick stuff to arrive at some answers, that's great. If you want to do a little bit of work with some of these steps, you can do that too. Some answers we can discuss as needed. Number 2, what do you guys think this is? Number 2, limit as x approaches negative infinity.
0.
Heading towards 0. Yep. You could use the degree trick there to help you with that. Or you could divide everything through by x cubed, like we did a minute ago. The answer there should be 0. Number 3 asks about what if the degree of the top is bigger? The answer to this one would be does not exist is actually valid, right? But if
Positive. Oh, negative infinity.
it's
sorry.
actually negative infinity, right?
Yes.
Because it's negative 2
Oh.
times,
Yeah, makes sense.
right? So I think we'd get negative infinity if we worked this all the way out, which is, of course, a non-existent value, right? It's a concept. But you could divide everything through by x and go through that process and see that you end up with essentially what amounts to negative 2 times positive infinity. And a really gigantic positive number times negative 2 ends up being a really, really big negative number. So, okay, and then how about the equation or the value of the horizontal asymptotes for that graph down there? What would you guys say? Y equals 2. Yep, exactly right. Y equals 2. And again, that would be arrived at by doing the limit as x heads towards infinity of 2x squared over x squared plus 4. And then technically, you'd also want to consider the limit as x heads towards negative infinity of the same thing. Ends up being in both cases a 2, but you technically want to consider both directions, right? Heading
It
towards
says
positive
find-
or negative.
It says find all horizontal asymptotes.
Mhm.
Can there only be one?
You can have 2. Yep.
Wait, can a horizontal asymptote approach two different values on each side?
Well, it depends on are you heading toward the right or the left.
So if you're going towards the
Sometimes
right,
you're heading towards the right, it might be like y equals 2, yeah, 4, and then if you're heading way to the left edge of the graph, it's y equals negative 1 or something like that.
what would be the difference? What would that look like?
It's just about the long-term right-hand behavior, left-hand behavior. It's not. Sometimes we think of horizontal asymptotes as being the same as vertical asymptotes. We're basically just saying as you head way to the left edge of the graph, where the value's headed, and the far right edge of the graph, where the value's headed. They don't have to head towards the same place. They often do. But they don't have to. I'll send you an email with an example. How about that?
Awesome, that too, please.
Okay. Okay, let's see here. How about optimization? We're going to continue to do a little bit of application here. Let's just make this a little review, see if we can fill in some blanks and make sure that we're all on the same page. You guys just say these, and if there's questions or pauses or whatever, we can talk. So finding an optimum value also means finding a blank or blank.
Max or min?
Max or min, yep. Okay, and blank, maxes and mins, occur at blank points or endpoints. What do you think goes in that blank? Critical points, yep. I'll just put crit for critical. And blank points, that would be critical points, are places where the derivative or the rate of change, or whatever it is blank or does not exist. So are these not the things we've talked about several times already in veterans ad nauseum, right? Over and over again. So I've given you some examples of some steps you might want to take here. Not going to read those to you. I think it's better to just try some and see how these steps weave their way in, right? So let's try to see some logic in these and see where we end up. We'll see what happens. Okay, so I would like to skip number 1, and I would like to go to number 2. Number 2 says, on a given day, the flow rate F in cars per hour on a congested roadway is given by that function, F equals, where V is the speed of the traffic in miles per hour. What speed will maximize the flow rate on the road? Okay, so I want to give you guys. Sometimes this one can be kind of confusing because F is a flow rate, right?
Is this like the freeze frame?
No, that's related rate stuff.
Oh, that's what I was thinking of. I saw some here too.
I thought that was this.
Oh.
So, anyways,
I don't know.
Oh, so you found a derivative.
so listen up. I want to give you guys just kind of a framework to think this through. If you're trying to find the maximum of blank, you need to set blank prime equal to 0 / DNE, right? So I'm trying to maximize flow rate, so I'm trying to maximize F. What would you say would be a good first step? Find F prime. I like it. What rule are you going to have to use to do that? Correct. So we're going to go with capital F prime, and I want you guys to do this on your own. I'll just do it quietly up on the screen, and we can compare in a minute. Once you're ready to check and see if we have the same thing, feel free. What do y'all think? The same thing?
Why didn't simplify
I went ahead and multiplied that last term and combined my like terms, right?
Yep, you just can't.
Okay, so you have minus 0.04 v squared. You can combine those two fairly quickly. And you really didn't have to do that. If you had that first line, obviously you've got a good derivative. Or at least we all agree, if that's the case. Okay. So y'all said that we need to find F prime as a good first step. Hopefully we're all there. What would we do with this right now? Set it equal to 0, yeah. And by the way, how do we know that the denominator could never be 0? Well, but the derivative, the denominator maybe could be 0. Like, how do we know that that's not even going to be a thing we need to be worried about?
You add 22 and then you have to do the square.
Yeah, squaring v guarantees that v is what? Positive times another positive plus positive 22 is positive. And that means the denominator in no way could ever be 0. It's going to be some positive number squared, so it's even more positive now, right? So there's no way that this could be a DNE, so that's why we just consider the equal 0. So then How do I solve an equation like this?
22 minus point.
Yeah, isn't the numerator the only thing that could really make the whole fraction 0? Yeah. So yeah, 22 minus this. And of course, for you guys, that makes this a lot easier, and you can use your calculator, get it done pretty quick. 22 minus 0.02 v squared equals 0. If I remember right, this is like 30-something. 166? Okay. So V equals 33.166. Okay, so can anybody identify what it is that we have actually found now? I've done some good math. It's a critical number, right. So this is a candidate. This is a place where the maximum flow rate might happen. And it's our only critical number, right? That's the only one.
There's no endpoints, so it has to be that.
And right, so there's no endpoints really to consider, although you could say that for speed, the left endpoint would be 0,
But then the speed would be 0.
but then there'd be no flow rate, right?
Yeah.
Which probably would not be a maximum. And then what's the upper end? Like how fast could a car go? There really isn't an upper end, is there?
Speed of light.
Speed of light, right? So 3.0 whatever times 10 to the something, or no, 186,000 miles per second, right? That's it. I think that's what it is.
3.0 times 10 to the 8.
That's what I was thinking. Meters per second, right? Yes. There we go. So the only thing that's left to do here is to confirm, indeed, that this is going to provide a maximum flow rate. What would you guys say would be your chosen method for doing that? Would you say first derivative test or second derivative test? What do you think? So I think either way could go. Like if you got the calculator active, you probably could use Math 8, right? And find what the value of the second derivative is at this 33 number.
Yo.
You could also just test a number on either side. I mean, I don't know that one or the other is going to be easier. I think that certainly would fall down to a matter of opinion. So, I don't know. Santi is doing his F double prime thing. Maybe somebody else might be doing first derivative test. I don't know.
Why not do the x equals?
I don't think you need to.
Oh, no, you don't.
I think I would just go Math 8 at 33.166, whatever. So, did you get a number for that, Santi?
I got a positive number. It's like 1.699.
Well, that doesn't sound right because we're looking for a maximum. So I'm thinking F double prime should be, if we're going to do that route, should be negative. Right?
Oh, yeah, okay.
Because that would make F concave down, which would make that critical point at a maximum.
That doesn't
Santi,
We are all floored, Santi. What'd you get?
-0.030.
Okay. See if Santi confirms that. So that number is negative.
What'd you get?
Negative 0.030.
Oh, yo.
Yeah, you're just doing Math 8 with F prime.
What the hell do you do?
Yeah. -0.0301511.
Okay. I don't know. I've typically done the first derivative test with this, so I don't have the number memorized. I don't have the first derivative test numbers memorized either. Okay. So assuming that that's the correct value,
Wrong.
we can say, therefore, F is concave down at V equals 33.166. Therefore, F has a max at V equals 33.166. So if we're trying to maximize flow rate, the traffic engineers would want to set the speed limit to be 33. Or maybe 35 or 30, right, to go with those multiples of 5. Although if you go to Target and Town Center, like the speed limit is like 12 and a half. Never seen that, but whatever.
In Town Center, like Torchy's and Shake Shack, it's 6 7/8.
6 and 7/8, even better. They're really making you think. You're like between 6 and 7, pretty close. Okay, very good. Would you guys move to the next one? The one about the farmer.
Oh, these are my favorite.
The one about the farmer. Yeah, I like these two.
That and Norman windows.
The Norman windows, yes. So fancy.
These are the ones I like. The farm
Yeah, this is a classic, right? This is definitely a classic. And this, of course, can take on all different shapes and sizes, literally. Sometimes the pastures get divided up into little segments. Sometimes it's like, a different shape and type. I mean, who knows? These can take on all kinds of things, all kinds of different shapes and concepts. This one says a farmer wants a rectangular pasture adjacent to a river. I remember last year I gave you guys a question on a quiz where it was like this guy wanted to create some fences for his two dogs because they fought a lot, and there was all these different divisions within the kennels and all that stuff. So these can be interesting to visualize for sure. So the pasture has to contain 245,000 square meters. What dimensions will require the least amount of fencing if no fencing is needed along the river? Picture is nice, right? If I was going to do this one and I'd never seen it before, I might be tempted to, draw the, I think I'll go with this. Yeah, I might be tempted to draw the river over here and, the pasture over here, like so. And then it says that there's no fencing needed along the river. So if I was going to draw this, I would say that my fence would go from here to here, then from here to here, and then right there. And I don't need that fence up against the river. So there's only 3 sides to this because, I don't know, apparently these cows don't want to walk in the water. Or they can't swim or something. Who knows? All right. So if we're going to be working with this, we got to admit we have no idea what the dimensions are for this pasture yet. So we should probably label them with variables. Any recommendations on what we could do? X and Y, right? I like that. I'd go X here and Y there just to be consistent with what these axes normally look like. But if you wanted to use L and W for length and width or B and H for base and height, that doesn't really matter. Bless you. Okay, so can anybody think of a relationship that I could write down that involves the X and the Y that's true and involves some of the stuff we have up in there that might be important?
245,000 equals X, Y.
Yeah, because we're talking about area, right? Yeah, so we could say XY equals 245,000. That's based on that area that we were given. It needs to contain that much pasture in there. But then we stop and think, well, what is it that we're trying to do? It says, what dimensions will require the least amount of fencing? So is that an area sort of a question? What is that more like? More of a perimeter, right? Like literally the amount of fence is kind of a perimeter idea. Of course, one side's open, so it's not strictly a perimeter of a closed figure at least. But it is kind of a perimeter. So can you think of a way we could express perimeter with those same variables?
2y plus x.
Yeah, 2y plus x is equal to the perimeter. I like it. So here's where we run into a little bit of an issue here. If we think to ourselves, awesome, I've got this thing set up. I'm trying to minimize, right? Least amount. Does that make sense for us? Least amount would be a minimum. So I'm trying to minimize perimeter. So why not just find P prime? What's the issue with where we currently stand with doing that?
You don't know X or Y.
Yeah, we don't know X or Y. They're 2 different variables. So it's going to be the question of, am I going to do dP dx? Am I going to do dP dy? Am I going to graduate to Calc 3 and do the partial with respect to X or the partial with respect to Y?
Yes.
Or we could just use substitution. Yay, there we go.
Yes, Queen.
Well done. So I could use my area relationship that I wrote first. I could use that then to help me substitute into my perimeter equation. So maybe we do this. We say y equals 245,000 over x. And I could then use that expression to substitute in for the y in the other one. So if I did that, I would get, I'm going to do a little arithmetic here, I'd get 490,000 times x to the negative 1 plus x equals p. I skipped a couple steps in there. Is that okay? I did 2 times 245,000 is 490.
Run it up.
490K. And instead of writing it as over x, I just went ahead and moved the x up. Why would I do that other than just to be fancy?
Easier to do than derivative.
I'm going to do a derivative here in a second, and it's going to be easier to do the power rule, right? Than some convoluted quotient rule or when you don't need to, right? Why bother when you don't have to even do that?
Which one is? Which one
So now all I need to do is write dP dx. And dP dx, of course, using a power rule, gets to be this and that. And so this is our derivative. Is there any value of x for which this derivative doesn't exist?
No, sir. Actually, I don't know.
Zero.
0, right? Because isn't it x to the negative 2 a denominator? But when you stop and think about the realistic domain of this question, if x is 0, what kind of a field does this farmer have? He has no field, right? Yeah, a lot of dead cattle or sheep or whatever because there's no grass. The fence has squeezed them, I suppose, whatever. So we're not going to consider the DNE aspect of critical points. We would consider simply the equals 0 aspect, right? So we'd set that derivative equal to 0. And believe it or not, this is at times where there's a great consternation and fear surrounding stuff like this. Like, gee, Mr. Anderson, I'm pretty good at derivatives, and I'm pretty good at the first derivative test, but don't you dare ask me to solve an equation like that. Scary, right? Any suggestions on what we could do to solve this thing? Well, we might do double prime later, but we need to find our critical point first.
No, make it, put it back into a fraction, take the one to the other side.
Oh.
Come on, guy.
Listen to this wonderful common sense. I love it. So, how about, now I'm going to skip some steps. Y'all okay with this? How about this? 490,000 over x squared equals 1.
Love it.
I flipped down and added over to the left side.
Yes, sir.
So if we did that, what would you do next?
X squared times.
Yay, multiply by x squared on both sides? Yeah. So 490,000 equals x squared. I'm sorry if I'm insulting you, but there have been so many folks that have gotten to this point and struggled, and you do not appear to be struggling, so that is awesome. We square root both sides now. That's the easy part. What do we get for x? Plus or minus, technically, but again, realistic domain tells us that a length of negative 700 really doesn't make much sense, and so we go with the positive square root here. What is that thing, by the way, the 700?
X.
It's x, but like, what is the meaning of it?
Oh,
Like the length of the-
I didn't quite hear what you said, Aiden.
700 meters, it's the,
Right, but in terms of the calculus process that we're thinking about.
it's the relative maximum.
Maybe. We don't know that yet, but we do know for sure that it is a critical number, right? So it might be the max, right? We just haven't confirmed that yet. We're really hoping that it is, right? So x equals 700 critical point. And I want to go back to Forrest's idea because I said, Forrest, what do we do with this? And he said, find p double prime to use a second derivative test. I think that makes the most sense. I really do. Because if I say p double prime would equal, what, 980,000 times x to the negative 3? Well, here's the thing. If I plug a 700 in for x, taking that to the negative 3, it's still a positive number, right? Times 980,000. I can say for sure here that p double prime of 700 is positive, right? If I plugged a 700 into your second derivative? I don't know. I mean, off the top of my head, I do not know what 980,000 over 700 cubed is. But I do know it's positive. I do know for sure that it's positive. What's that?
You have that stuff memorized.
I should. I'll work on that. Maybe someday. So if p double prime is positive at my critical point, what does that mean about p? Relative min at that particular spot. So we can say, therefore, p is minimized when x equals 700. And it did ask for the dimensions, and so the dimensions, of course, would be both the x and the y. So if x is 700, y is, you said 350? So we'd say, therefore, y is 350. That would give the full dimensions of this pasture. Okay, so here's the deal. Can you guys keep a secret?
It depends.
This is not like a scandalous secret, really. But it is a real secret. You're not supposed, like, so if you blab, then you're the one that blabbed. So tomorrow there's a fire drill. And the fire drill will occur towards the end of our class. Like towards the end of purple. As we know, the first fire drill probably will bleed into gray for sure. But there is, so the part you're supposed to keep a secret is don't go around and saying, hey guys, there's a fire drill tomorrow. It's supposed to be like a surprise. So I'm telling you this, though, so that you know what we're going to do tomorrow is we'll probably do another one of these max-min style questions. We'll probably only do one of them, and then we'll catch a little bit of like the tangent line approximation differential stuff, and then I'm sure that'll be our time. So I just thought I'd let you know that ahead of time. So if you're on the ball, print off the Unit 2, Chapter 4 stuff, and have that ready, but we won't do that until next week. So have a good day. Enjoy your lunch.
That's Thursday, right? That's Thursday.
Test should be Thursday. Yep.